Here we go. This is section 6.2 in our book. This is our last lecture on differentiation. So on Monday, we're going to start up with integration. We have a quiz on Wednesday. That quiz is going to stop with today's lecture. Okay, so the quiz is basically going to be up through differentiation. So for that quiz, we're not going to do what we do on Monday. Okay? So
starting from what? Like what content will the quiz cover?
In theory, the quiz could cover uniform continuity and monotone and inverse functions. Okay. Because those actually never got covered. But the bulk of the quiz will be about differentiation. Yes, Daniel, 5.4 to 6.2, that's correct, for the quiz on Wednesday. Okay, so today is the mean value theorem. So first, okay, so there's a ton of results today. We're not going to prove them all. I hope to prove the first three. The proofs are all very short, but there's a lot of them. So we need a definition first. Let's take an interval, I, and let's have a function defined on that interval. And here is our definition. It has a local or a relative maximum at the point C. Well, if at C there is a neighborhood such that f of C is greater than f at anything else in the neighborhood, and remember the way we formalize neighborhoods is we usually say there's a delta. Okay, so if there is a positive delta such that f at C is larger than f at x, for all x in the interval which are within delta of C. Okay. There we go. There's our continuous. That's a pretty bad continuous function. Let me try again. Okay. There's our continuous function. That is our local max. Okay. There is some delta so that within delta of C, f of C is the largest value of the function. Okay. I hope this is a familiar concept from Calc 1. The book calls it a relative minimum. I'm used to calling it a local minimum. I think I'll do local minimum, but just realized the book uses relative minimum. They both mean the same thing. Okay. I'm not going to bother defining relative. Oh, sorry. This is a relative maximum or a local maximum. I'm not going to define local or relative minimum because it's completely analogous. You just flip the inequality there. Benjamin asked a good question. Why do we use an interval here and not an arbitrary subset of R? Yeah. I actually did have this as an arbitrary subset of R earlier. All of our results in this section are going to be for intervals. And after our first result, they really need to be for intervals. So we're just going to do intervals the whole section. Okay. just so we don't. So we're going to stick with intervals so we don't confuse anything. Okay. Now, let me note we've already defined absolute maximums and minimums. We did that back in section 5.3. You might remember our theorem back then. It was the maximum minimum theorem. It said if you've got a continuous function on a closed and bounded interval, then it does attain its maximum and its minimum. Okay? But these are different. These are local maximums and local minimums. Okay. So what is the Calc 1 theorem that you remember about local maximums?
They occur when the derivative is equal to 0.
Exactly. So let's prove that first. Okay. So what are we going to have to do? Let's take an interval. Let's take a function from that interval to the real numbers that has a local maximum. Now, our definition of local maximum is really not good for endpoints of the interval. Okay, so we're basically just going to have to ignore endpoints. So we're only going to look at interior points. Okay, so I want to assume that I've got a local maximum at the interior point, C. Okay. So interior point, literally all that means is it's not an endpoint of the interval. Okay. Now, we would like to conclude that our derivative is 0 there. Okay, but there's a slight problem. Our derivative might not exist there. So we need to add another hypothesis that we are differentiable there. Then, if f is differentiable at C, its derivative at C is equal to 0. It is the first derivative test. So if you think about finding all the local maximums or minimums of your function on an interval, this takes care of all the points in the inside where the function is differentiable. You'd also want to check all the points where your function isn't differentiable. And you'd want to check the endpoints. Generally in Calc 1, you didn't have any of those points where it wasn't differentiable. Okay, so let's prove this. Let's just do this kind of blanket statement. Let I, F, and C be as in the statement of the result. And suppose we have a delta, let's see, is such that f of c is greater than or equal to f of x for all x in the interval. Which are within delta of c. Okay, because we're assuming that f has a local maximum at C. Now, we know that f is differentiable there. So f prime at C is, I'm just going to write in the definition. Of the limit. Okay, so I'm saying we know that this limit exists. Now, once you know a limit exists, that means that no matter how you approach the point, no matter how you approach this point C, you'll get the same answer. And so let's approach it from the left and approach it from the right. Now, we skipped the one-sided limits, but that's okay. We're just going to use sequences to do this, okay? Let me go up here. Because C is not an endpoint of the interval, we can find a sequence from the interval such that a few things. I want it to converge to C. I want it to converge from the left. So I want all of these things to be to the left of C, which means less than or equal to C. In fact, we want them all to be less than C. We don't want them to be equal to C. Okay, that's for all n. And finally, we want them to all be within distance delta of C. Okay. Now, we know that our limit exists, so f prime at C would have to also be the limit when I plug in the sequence. This is a sequential form of the limit is what we're using here. Right? Now, what is the sign of the numerator of that fraction?
Should be negative.
It's not positive. How about that?
Okay, right, not positive.
What about the sign of the denominator?
It would be negative, correct?
Yes, that one is strongly negative, strictly negative. Okay, so our fraction is non-negative. Right? So every term in that fraction is non-negative, and so the limit is going to be non-negative. Okay, that was either a homework problem or an easy proposition we proved earlier. Okay? Any questions about that?
How do we know the denominator is less than 0?
That is because the xn's were all to the left of C. So you could just literally take this inequality up here and subtract c from both sides. And you'll get xn minus c is less than 0.
Excuse me, do we actually have a theorem that says we can find such a sequence?
No, we don't. We don't have such a theorem.
Okay.
But this would be easy to do. Right. We could actually just write down the sequence, right? We could literally say, let's take xn to be c minus, I don't know, delta over 2n. Does that satisfy all of these things? It converges to c. Yep. All the terms are to the left of c. Yep. And they are all within delta. Yep. Okay, so we don't have a theorem that says we have the sequence, but we can just write it down. So we definitely have the sequence. Cool.
That's clear.
In fact, I'm gonna make a note to change the notes. We should just, instead of saying we have this sequence, we should just do that. And let's do it for the other side here. Now, considering, let's just go from the other side. So we'll do c plus delta over 2n instead. And again, we're using the sequential form of the limit, and it just says that we put in a sequence that goes to c, and we have to get the same answer. Okay. Now when we plug in this sequence, what's the sign of the numerator?
Not positive?
Yep, less than or equal to 0, and the denominator?
Positive.
Positive. So this limit is less than or equal to 0. And there we go. We've shown that the derivative is greater than or equal to 0 and less than or equal to 0. So it had better be 0. Okay. Any questions about that?
This is more of a general question.
Mm-hmm.
So since we didn't use or we didn't develop these one-sided limits, we can instead just use the sequential form and construct some sequence that does this sort of one-sidedness.
Yeah. Yeah.
Okay.
Oh, yeah, how do we know these these points are in the interval I? You know what we should have done? We should have chosen our delta so that okay, so yeah. That's a good question. So let me say two things. First of all, it doesn't really matter. Eventually these terms will be in the interval. So the thing about the limits is still going to be true, because eventually they have to get close enough that we're in the limit, because we're not at an endpoint. But we could have chosen delta so that actually that whole neighborhood is inside the interval. Okay. That's what we should have done. Okay?
And we're guaranteed that we can pick a delta because it is an interval and C is a cluster point.
So, right, the reason we can do this thing I wanted to go back in time and do is because it's an interval and C is not an endpoint. If C were an endpoint, we couldn't do that. Okay? So, two comments about this theorem. Obviously, if you wanted to do it for relative minimums instead, that would be just fine. Let's see. With a relative minimum, your numerators would flip signs. Okay, but everything else would be the same, and so you'd get less than or equal to 0, and then you'd get greater than or equal to 0. You'd have the same conclusion, okay? Or you could just apply the same exact theorem to minus f instead of f. Okay? The other thing, let me point out that the converse of this proposition is not true. Okay? So it is not the case that wherever you have a relative min or max, your derivative has to be equal to 0. Okay? So obviously you could have like f of x equals absolute value x, right? And so we have a relative or a local min at 0, but we don't have a 0 derivative there because we don't have a derivative there. Okay. Good. Let's move on. That was our first result. Now our proofs get faster here because there's less to prove. That was the heavy lifting. Now we just have to use it. Does anyone remember Rolle's theorem?
It's, to put it colloquially, it's like the mean value theorem, only your function looks nice and straight, so to speak.
Mm-hmm.
A nice little arc. Something like that, I think.
Yep. It is actually a special case of the mean value theorem. Except we're going to use it to prove the mean value theorem, and basically everybody uses it to prove the mean value theorem. In fact, it shows up in a ton of proofs. We're going to use it, it looks like next semester we're going to use it to prove things about Taylor series too. Okay, so suppose you've got a function on a closed interval. Okay, this is where that previous result, we could have done it for an arbitrary set as your domain, but now for the rest of the lecture, we need an interval, or else these things start being false. So you get a continuous function on a closed interval, and it's differentiable on the open interval. Okay. And the other hypothesis is that it's equal, and there's equal values on both ends of the intervals, on both ends of the interval. And the conclusion is that there is at least one point with a 0 derivative inside there. Okay, so there's at least one point C in the open interval whose derivative is 0. F's derivative is 0 at that point. Okay. Now, this is going to come together really quick from all the things we've proved. We already mentioned this once today. By the maximum minimum theorem, f is a continuous function on a closed and bounded interval. So f has an absolute maximum and an absolute minimum. On the closed interval. Okay. Now, there's kind of two cases here, but we don't really need to split them into two cases, but we'll talk about them here. Could f of a and f of b... Let me write my sentence first. Let's try that. Because f is the same at a and b, my claim is f must have at least one local or relative maximum or minimum at a point inside the interval. Okay, so let's see why that sentence is true. Okay, so my question is, why is that true? Are there any volunteers?
It's true in the case that is a little tricky is when f of a is equal to f of a equals f of b equals the minimum and the maximum. Mm-hmm. And then you get a flat line. Yes. And then you just pick any point.
Yep. So the point is, f of a and f of b, they might be neither the maximum, the absolute max or the absolute min, in which case you've got both an absolute min and an absolute max inside. Okay, then you're fine. Or f of a and f of b they could both be the absolute max, but then if they aren't the absolute min, you've got a relative min, a local min on the inside. Or if they're not the absolute max, then you've got a relative max on the inside. And then finally, if they are both the absolute max and the absolute min, then that means the function had to be constant. And since it's constant, all the points are local maximums and local minimums on the inside of that interval. Okay? Well, once we've found a local max or a local min on the inside of that interval, we're done by the previous result, right? Because our previous result set our derivative 0 there. Okay. Proof seems really short, but of course we use this maximum minimum theorem. That, by the way, if you want to go look at it, that was theorem 5.3.4. Okay. Are there any questions before we move on to the mean value theorem?
I have a quick question. I can't seem to
Sure.
find it in my notes right now, but for our proof of the intermediate value theorem, is it weak or strong? Like, do we include the endpoints as part of it or not? I just can't find it right now. Like, do we guarantee there's a point in the interior or just on the interval as a whole with the IVT?
On the interior, I believe.
Okay, so then we could even use the intermediate value theorem to say that, you know, we obtain the value FA equals FB, right? We wouldn't even have to do anything too tricky.
Oh, I'm sorry. Yeah, you just convinced me that what I said was wrong. Yeah, the intermediate value theorem allows the values to be at the ends. Because you clearly can't do what
Okay.
I think you're suggesting, because if you think about like f of x equals x squared.
Okay, right, and then you don't get one in the interior. Okay.
Right.
Okay.
Okay. Well, so finally our main result today. Now that we got Rolle's theorem, we're going to do the mean value theorem. So Rolle's theorem is a special case of the mean value theorem, but we prove the mean value theorem using Rolle's theorem. So again, it's our standard hypothesis for today. We get a function on a closed interval. It's continuous. And it's differentiable on the inside. There's your statement. Now, equivalently, we could write f prime at c is f of b minus f of a over b minus a. Okay, we just tend to write it in this other way. Okay, and the geometric intuition for this is that you've got some function, and you're taking 2 points, and you're going to connect them with the line. Okay, so that's my A and that's my B. The slope of that line is f of b minus f of a divided by b minus a, because it's, you know, just your rise over run formula, or however you learn to call it. Okay, and the mean value theorem says somewhere in here there's a point whose tangent line has the same slope. I don't know, I'm going to call it that point. Okay. Okay, now we're going to prove this using Rolle's theorem. So I need Rolle's theorem applied when the function had the same value on the two ends of this interval. So I'm going to define a new function that does have the same value on the two ends of the interval. So we're going to define this function phi, and it is f of x minus f of a minus f of b minus f of a over b minus a times x minus a. Okay. Now, this function is continuous on the closed interval. Okay. Why is it continuous on the closed interval? Well, just our rules of continuity. F is continuous there. So let's say f of x is continuous on the closed interval. F of a is just some constant. F of b minus f of a over b minus a, that's just some constants. X is continuous, and then a is just some constant. Okay? So it's clearly continuous on this closed interval, and it's differentiable on the open interval. Okay, it's differentiable by our rules for differentiation, because f is differentiable there, and then again, f of a is a constant, f of b is a constant, blah, blah, blah. And what is its, what's phi of a? Well, just plug in an a for x, and you'll see everything goes to 0. Okay. I claim that's the same as phi of b. Why is that true? Well, plug in a b. Now it's a little bit not quite as obvious, but you'll get f of b minus f of a minus, and then you'll get an f of b minus f of a divided by b minus a, but then times b minus a, so everything cancels out. Okay. So now, Rolle's theorem says there's a point where the derivative is 0. Okay, so phi prime of c has to be 0. Okay, but then what is the derivative of phi? Well, we just use our rules for derivatives. The derivative of phi is, we just go look at it. It's the derivative of x minus, and then that constant drops away, and then minus, we get this quotient times 1, and I realize I made a mistake here. I shouldn't have written the derivative at x. I should have written the derivative at c. Okay, that is phi prime at c is f prime at c minus that. Well, that's it, right? So we've proved there's a point C where f prime at c is equal to f of b minus f of a divided by b minus a. That is what we wanted to prove. So that we proved is the same thing we claimed in the statement. Okay. Any questions on the mean value theorem? Yeah. Okay, so notice, by the way, that I said Rolle's theorem is a special case, and you see, oops, if f of b and f of a are the same thing, then we get a 0 there, and so f prime would have to be 0. Okay. Now, we've got about 8 minutes left of class, and I have 3 corollaries left to do. So I think this is an impossibility, but we'll see. We'll see what we can do. Corollary 1. Standard hypotheses of today. F is a continuous function on a closed interval, and it's differentiable on the inside. If its derivative is 0 the whole way through, then it's a constant function. In fact, it's a constant function on the closed interval. Okay, so, that first line is just our standard hypotheses for today. The second line is what the theorem actually says, what the corollary actually says. I'm going to try and sketch the proof of this. Take some point. I'm going to take some point x it's in this half open interval. Okay, so I'm not going to allow it to be a, but it can be anything else in the closed interval from a to b. And I want to show that f of x is equal to f of a. Okay, and that'll do it. I already know that f of a is equal to f of a. Well, by the mean value theorem, there is a point C I should probably explain this. I want to actually apply the mean value theorem to the function f on the closed interval from a to x. Okay, it satisfies the hypotheses because it was continuous on a bigger interval and it's differentiable on a bigger interval. So we're okay. Then we'll get a point C in the open interval from a to x, which satisfies f of x minus f of a equals f prime at C times x minus a. Okay, but we have said that f prime is equal to 0 for all the points here. That's it. Right? Since the derivative is 0, f of x has to equal f of a. Good. So if your derivative is 0, you are constants. If you think about that, it's a priori. If I asked you to prove that, it would be a pretty. That'd be kind of mean. What would be meanest is if I waited till the end of the course and I asked you to prove it. You'd probably look at that statement and you'd want to integrate. Okay. Right, because you'd say, well, I want to integrate the function 0. I think, I guess that proof would work. Although this is even better using the mean value theorem. We don't even have to know what integration is in order to get this conclusion. Okay? Okay, that's corollary 1. Now we have 3 minutes left. So corollary 2. Suppose we get two functions. Again, they're on a closed interval, they're continuous, and they're differentiable on the inside. If the derivatives are equal, then they differ by a constant. Okay, so then there is some constant. So that on this interval, f is just g plus that constant. Okay. This corollary, it doesn't even deserve an attempted proof. You just need to take f minus g and you apply the previous results. If you look at f minus g, its derivative will be 0, and so you'll find out that f minus g is a constant, and therefore f is g plus that constant. Good? Now, last corollary. I'm going to state the corollary. It deserves a little bit of a proof. I'll be posting the lecture notes in a little while. I'm going to make a few changes to them, as we noticed today. So this proof will be in the lecture notes. I'm not going to have a chance to finish it today. Okay, let me just state the corollary. If f is a function on a closed interval, in this case, I'm going to go with slightly weaker hypotheses. I'm just going to say it's differentiable in the middle. So what have I dropped? I've dropped continuity at the endpoints, but because we don't need it. Then f is increasing. And by increasing, I mean on its domain, which is this closed interval. If and only if its derivative is positive on the inside. Okay. We actually haven't defined increasing formally. The formal definition will be in the lecture notes. I hope we can just go with the informal definition. Other than that, Right, so obviously this is a classic Calc 1 result, and it just follows from the mean value theorem. Right, you end up just looking at this kind of thing. Well, I mean, okay, so this is one direction. If x is less than y, then by the mean value theorem, f of y minus f of x is a derivative at some point in the middle. Well, that derivative has to be positive, because that's our hypothesis. Y minus x, that's positive, because we assumed that x is less than y. So f of x, f of y minus f of x is, well, it's non-negative, and that's what an increasing function is. Okay, so that's one direction of the proof. The other direction of the proof is that if you are increasing, then your derivative is always non-negative. And that takes a little more work. I'll leave that for you to look in the lecture notes. Okay, so I will end the lecture there. Just a slight correction after class ended. I messed up the hypotheses on this theorem. The function needs to be continuous on the closed interval in order to get the conclusion. To see a contradiction to how I first wrote it, just consider this function 1 over x when x isn't 0 and 0 at 0, then, well, you just look at the decreasing version of the corollary. Right, f isn't decreasing on the entire closed interval 0 to 1. But if you fix the statement of the corollary and you insist that it be continuous on the closed interval, then this function is no longer a counterexample because it is not continuous on the closed interval 0 to 1.